All right, welcome back to the deep dive. We love getting into the core concepts that really make a difference when you're building software. And today we're going to be looking at how data moves around within a system, especially as things get more complex.
Yeah, you can kind of think of it like the circulatory system of a really complicated application, right? You got to get the data where it needs to go.
Absolutely, and that's crucial for anyone, especially if you're, aiming for that senior software engineer role. And I know a lot of you listening out there are probably prepping for those technical interviews, brushing up on system design. So this deep dive, this is going to give you some awesome context on how data flows in different ways.
That's right. You're probably already thinking about, things like REST, RPC, databases, all
Right.
these different paradigms.
Exactly. And today we're adding another tool to your toolbox, message passing systems. It's kind of a cool blend of those familiar approaches, and we're going to unpack how it works and why it's so powerful.
Yeah, and especially in those distributed systems where you've got things spread out across lots of different machines, message passing can be a real game changer.
Totally. So for this deep dive, we're zeroing in on message passing systems.
hmm
What makes them tick? What are their strengths? And what are the things you got to watch out for, especially as you're designing systems that need to scale?
All right, let's start by drawing some clear lines between message passing and those other ways of moving data around that you mentioned. The REST and RPC, those are all about that quick back and forth exchange.
Yeah, you make a request, you get a response, right? Like a phone call, almost instant.
Exactly, low latency, direct connection. Then you've got databases, which are a whole different animal. You store data at one point in time and someone else comes along later and grabs it. There's this separation in time between the writer and the reader.
Right. It's not that immediate interaction like you get with REST or RPC.
Now, message passing systems are kind of interesting because they combine aspects of both. You still have that aim for speedy delivery, like with RPC, but you introduce this middleman, a message broker that acts as a go-between for the sender and the receiver.
Okay, so a message broker that sounds like a key player here. What's the point of adding this extra step instead of just going direct like in RPC?
Well, that extra step actually brings in a whole bunch of benefits, particularly when you're building systems that need to be super reliable and able to handle lots of traffic.
That's what we're all striving for, right?
Exactly. So think about reliability first. Let's say a service that's supposed to receive a message is down for a bit, maybe it's overloaded or being updated. With a message broker in the mix, it can hold on to that message until the service is back up and running.
So it's like having a really dependable mail carrier who won't lose your letter even if the recipient isn't home. Makes sense for building tough systems. What else does this broker bring to the table?
Automatic redelivery. Imagine a service gets a message from the broker but crashes before it can fully process it and say, hey, I got it. A good message broker will resend that message once the service comes back to life.
That's huge for preventing data loss. But I imagine there's a catch, right? What if the message gets processed twice?
You're thinking like a senior engineer already. That's a crucial point. You have to design your services to be idempotent, meaning that processing the same message multiple times has the same effect as processing it just once. That's one of the things you trade off for that extra reliability.
Got it. So the broker handles the retry, but you, the developer, have to ensure things don't get messed up if a message is accidentally processed twice. You mentioned something else earlier. Senders don't need to know the exact network addresses of the recipients. Why is that such a big deal?
Especially in cloud environments where things are constantly changing. IP addresses, virtual machines popping up and down, it's chaos. But with a message broker, the sender doesn't need to keep track of all that. It just publishes the message to a well-known queue or topic, and the broker figures out where to send it.
So it's like having a smart postal service that can reroute your mail even if the recipient moves. Keeps things flexible, right?
Yeah, you said it. No more rigid connections, which is awesome for building scalable systems where services can come and go without bringing the whole house down.
And you mentioned sending a single message to lots of recipients. How does that work?
That's where topics come in, sometimes called publish-subscribe. You publish a message to a topic, and any service that's subscribed to that topic will get a copy. Think of it like a radio broadcast. The sender doesn't care who's listening. It just sends out the signal.
So it's a one-to-many communication model, unlike the one-to-one we usually see with RPC. That opens up some cool possibilities.
Absolutely. It's a fundamental shift in how you think about communication between different parts of your system. For instance, you could have a topic for new orders, and any service that cares about new orders can subscribe to it and react accordingly.
Right, so different parts of the system can stay in sync without needing to know about each other directly. Pretty powerful stuff. You did say earlier that message passing is usually a one-way street, unlike the request-response setup of RPC. Can you walk us through that a bit more?
Yeah, at its core, message passing is asynchronous. When a service sends a message, it doesn't sit there waiting for a reply, it just sends it off and keeps going. But, and this is important, you can totally build request response on top of this.
So it's like sending a letter with a self-addressed stamped envelope so the recipient can send a reply back.
That's a good analogy. You basically include a reply to field in your message, telling the receiver where to send their response, and the sender listens on that specific channel.
Okay, so while message passing is inherently asynchronous, you can build in that synchronous back and forth if you need it. It's a bit more work than just a straight RPC call, but it gives you the advantages of asynchronous communication. You were talking about the history of message brokers earlier. It sounds like there's been a lot of movement in that space.
For sure. In the old days, it was mostly big commercial software, expensive and kind of clunky. But now, open source message brokers are taking over. You've got RabbitMQ, ActiveMQ, HornetQ, Nats, and of course the big one, Apache Kafka. These are names you're definitely going to hear in those senior level interviews.
Oh yeah, knowing your way around those is definitely a plus.
Yeah.
Can you give us a quick rundown of how these brokers usually work? What's the general model that's good to have in your back pocket for those interviews?
Sure. You've got services that act as producers, creating and sending messages. These messages get sent to specific queues or topics within the broker. On the flip side, you have consumers or subscribers listening to these queues or topics. The broker's job is to make sure those messages reach the right consumers reliably, whether it's a one-to-one delivery with a queue or a broadcast to multiple subscribers on a topic.
Right, so it's like a well-organized mailroom, sorting and delivering all the messages to the right places.
Yeah.
Now, what about the actual content of the messages? Any rules about what you can and can't send?
Generally, message brokers are pretty chill about that. They treat messages as just bytes of data, usually with some metadata attached. So you can use whatever data format makes sense for your application, whether it's JSON, XML, protocol buffers, you name it.
That flexibility is nice, but I can also see it becoming a headache, especially as systems evolve and change over time. If everyone's using different formats, things could get messy.
Yeah, and that's where the senior engineer thinking comes in. Because producers and consumers can be developed and updated independently, backward and forward compatibility is paramount. You got to make sure that changes to your message format don't break existing systems.
So it's kind of like database migrations, just for messages. Any tips for keeping things smooth as your message passing system grows?
Absolutely. The big one is design for change. Make new fields in your messages optional so older consumers don't freak out. Newer consumers should be able to handle messages missing those new fields. Versioning your message schemas is another good practice.
Right, it's all about planning for the future. You also mentioned something about preserving unknown fields. When would that come into play?
Let's say a consumer receives a message with fields it doesn't recognize but needs to republish it to another topic. You don't want to accidentally drop those fields, even if you don't understand them, because another service down the line might need them.
Makes sense. Don't discard information unless you're absolutely sure it's useless. Okay, let's switch gears a bit and talk about distributed actor frameworks. They sound like another piece of the puzzle for managing data flow and concurrency. How do they fit in with message brokers?
Okay, so first let's talk about the actor model itself. It's a way to handle concurrency within a single process without messing around with threads directly. You have these independent entities called actors, each with their own little world of state that no one else can touch directly. They talk to each other by sending messages, and it's all asynchronous, so no one's waiting around for a reply.
So it's like a bunch of little self-contained programs running side by side within a bigger application.
Exactly. And one thing that's interesting about the actor model is that even in a single process, message delivery isn't always guaranteed. Messages can get lost.
Sounds a bit risky, doesn't it?
Well, it actually reflects the reality of distributed systems, where networks aren't perfectly reliable, and it forces you to design your actors in a way that they can cope with those kinds of failures. Now, when you take this actor model and stretch it across multiple machines, you get distributed actor frameworks.
So instead of all the actors living on one computer, they can be spread out across a network.
Right. And the cool thing is that from the developer's perspective, it doesn't really change how you write the code. You send a message to an actor, and the framework handles all the magic of sending it over the network, serializing it, deserializing it, all that stuff.
So you can focus on the logic of your actors without getting bogged down in network details.
Precisely. And that built-in acceptance of message loss that I mentioned, that makes the actor model a great fit for distributed environments where things can and do go wrong.
So it's like it was designed with distributed systems in mind, with all their inherent unreliability.
Exactly. Now, about the connection with message brokers, distributed actor frameworks often bake in the functionality of a message broker right into the framework itself. So you get the concurrency model, the actor management, and the message transport all in one package.
Ah, so it's a more integrated approach compared to using a separate message broker.
Mm.
But you still mentioned that backward and forward compatibility is a concern with actor frameworks, even with all this fancy stuff going on. Why is that?
Well, think about what happens during an upgrade. You'll have different versions of your application running at the same time, and actors on different versions need to be able to talk to each other. If the message formats change in an incompatible way, you can still run into trouble.
Right, it's the same fundamental problem of making sure that data can be understood, even as systems change over time. So, how do different actor frameworks handle this compatibility challenge?
Let's take Akka, for example. It's popular with Java and Scala folks. By default, it uses Java's built-in serialization, which isn't always great for compatibility. But Akka lets you swap that out for something like protocol buffers, which has much better support for schema evolution, so you can upgrade more smoothly.
So Akka gives you options. What about Orleans, that .NET framework?
Orleans is a bit different. It has its own binary encoding format, which is fast, but not so good for compatibility. Upgrading usually involves setting up a whole new cluster and moving traffic over, which can cause some downtime. But like Akka, Orleans does let you plug in custom serialization if you need more control.
Okay, so Orleans is optimized for speed, but might require more work for seamless upgrades. What about Erlang OTP? It's known for building rock-solid systems, right?
It is, but even Erlang has its quirks. Their main data structure, called a record, can be a bit rigid when you need to change things. Rolling upgrades are doable, but you have to plan carefully and sometimes write extra code to handle the transitions.
So no matter which way you slice it, whether it's message brokers or actor frameworks, thinking about how data evolves is crucial for building systems that can stand the test of time.
That's the takeaway. Knowing the ins and outs of these different data flow methods, RPC, databases, message passing, actor frameworks gives you a huge advantage when you're designing systems, especially at the senior level.
Exactly. And for anyone prepping for those senior interviews, being able to explain these concepts, compare them, and talk about the trade-offs, that's going to show that you're ready for the big leagues.
What's really cool is that each of these approaches has its own strengths and weaknesses. Message passing brings that extra reliability and flexibility, while actor frameworks offer a really elegant way to manage concurrency. But you got to be smart about data compatibility with both.
All right, so to wrap things up, with all these trade-offs in mind, when do you think asynchronous message passing really shines? And what are some of the traps that a senior engineer needs to watch out for when designing these systems? Think about that as you continue your journey towards that senior role. Thanks for joining us on The Deep Dive.